Hey everybody, welcome to Think Like a Postgres. This is a little side project I've been thinking about for a few years. I actually saw a presentation right around the start of the pandemic that was really about SQL Server, and it talked about how SQL Server worked and how you could think like SQL Server. And I remember thinking at the time, like, boy, I wish somebody would do this talk, but like a Postgres version of it, right? And really kind of bring those things together on the Postgres side. And if you fast forward a few years, here we are. Nobody has done it, and I had some time on my hands, so I figured, hey, why not me? I'll give it a shot. In particular, what I really like about the way the talk is laid out, and what I really like about putting this one together, is the focus isn't so much on like tables and queries and the tools of Postgres. It does talk about that stuff. That stuff is important. But what I really like is how it focuses on the underlying data structures that Postgres uses when it tries to answer your queries and when it needs to get data. In particular, it really goes down to the page level. Postgres stores its data in 8K pages, and we take that knowledge and talk about how it stores that and tie that back in to your normal everyday queries and other usage. The database we're working with is a sample database that is actually based on the data from Stack Overflow. Figure most people probably know what Stack Overflow is. I think it's the largest question and answer site on the internet. It's certainly got to be the largest copy and paste source code repository out there. But if you're not familiar, basically, like I said, it's a question and answer site. There's all different versions of Stack Overflow, but most popular one is on tech and tech related questions. And what's really great is because all of this content is user generated, the folks at Stack Overflow, they actually produce a data dump of their database. Creative Commons licensed and available for anyone to go get. I put the URL on the screen there. Archive.org has different copies of it going back over time. And the version that I've taken, they put it out in a few different formats. The one that I've used for Postgres purposes was the XML dumps that they do. And I've taken that XML, transformed it, and created a schema that you would likely use if you were going to have that database in Postgres, and loaded that into a Postgres database. The Postgres I'm using happens to be Postgres 14.4. The good thing about what we're going to talk about today is it really talks at a more fundamental level. So regardless of what version of Postgres you're working with, this should apply to the systems that you're working on. There are a couple of features that you probably need to have at least Postgres 11, I would say, to make sure that you can use that. But hopefully everybody's working on 11 now. Postgres 10 is just about end of life at this point. So I'm gonna pretend like I know everybody upgrades on time and everything super smooth. It's great. Yeah. Anyways, so if we look at our Postgres version of Stack Overflow, dubbed here PG Overflow, and we just were to list out the tables of PSQL, what you would see is, just there's a few tables that they give you, like badges. You earn badges based on questions that you answer and things like that. The post table is actually both the table for questions and answers. Both of those are different types of posts. Gonna not comment on the sanity of the schema in particular, but it's a popular schema, and there's a lot of good questions out there that people use and tooling built around that. In particular, what we're going to focus on today is the users table. And this is, it's pretty straightforward. There's an ID column, which is the primary key. It's just, serial incrementing integer. For every user, they have an ID. There's other things like reputation. You earn reputation for answering questions or for asking really good questions. You can get reputation points for that. There's a last access date, like an about me, put your profile in, that kind of thing. And some other columns as well. So that users table, like I mentioned before, the way that Postgres takes that data that's in there, right? This is the schema portion of it. If you look at that schema and see the way those columns are written into the schema, the way Postgres actually stores that on disk is basically the same way. It takes the same order of columns and stores that, in pages on disk, essentially, right? Virtual pages. If you were to think about those pages, and you could, they're very much like if you had a spreadsheet, right? You could print those pages out. Here's kind of an example. If I were to print a page out and see what it looks like, this is an 8K page printed out onto paper, and you can just think of it as stacks and stacks of 8K pages. Now, in Postgres, you'll often hear the term heap used interchangeably with the word table. This basic piece of data where Postgres is storing its data, people refer to that as the heap, right? Your data is stored in the heap, different from, say, like in an index or something like that. So you'll hear that term a lot. And within the heap pages that you have, there are some metadata columns, and I've included a couple of them here. I didn't include all of them, there are some other ones. But I wanted you to be able to see the idea that, like, okay, we've got some metadata, and then again, it's just the columns laid out just like we have in our table ID, creation date, display name. It's also important to remember that the data that's in here, while the columns are in kind of a fixed order that aligns with what the table looks like, the data inside of it is not stored in any particular order. Whatever was the first row that came in is the first row that got written, and when the next row came in, it just writes that row after it, and so on and so on. When Postgres runs out of space on a page, right, when it gets more than 8K worth of data, it goes ahead and it writes, creates a second page, prints out another piece of paper, and starts writing on that one, right? So like I said, stacks and stacks of these 8K pages. Along with the metadata columns, there's also another little trick I just want you to be aware of. If you think about the About Me column, is probably the best example of this. In Postgres, you can store data. It's very common to store it as just a text field. Right? Other database systems, and in schema, I would say legacy schema, tend to see a lot of use of char and varchar fields, or char and varchar fields, or a mix of all four of those. In our database here, I've just created these things as text fields because that's really all that you need. And you see that a lot in Postgres. Now, the thing about those text fields is if you have enough data put in them, right, we only have 8K that we can put on a single page. So if you have enough data in a particular column, Postgres, what it will do is actually print a portion of that data along with a pointer out to another set of 8K pages, and that's where it stores the rest of that data. And I mention the About Me because if you look at certain people's About Me columns, some of them, the About Me is very short, right? Like, I live in Florida or whatever. It's something short. Other people think like that's a good field to put their magnum opus on how everything is wrong with society, and not that everything is right, but maybe that's just not the best place to put such a document. So I don't want you to get hung up on that. We're not going to go too deep into that specific thing, but just be aware if you use lots of text fields, not so much the text field, but if you start jamming large amounts of data into a text field like that, or you start using other types like JSONB or something like that, if you start storing larger pieces of data in a single column, there can be this additional bit of overhead. And if you're wondering, you want to read more about this process, this is known as toast in Postgres parlance. That's what it's called. These are toast tables where those other pages will be. But for now, we're going to concentrate on just the main heap of the users table, right? The simple rows going across, and let's talk about that. So if you imagine that we have these 8K stacks of pages, one stack of pages, right? For every stack of pages that you have, it's one stack per object. So we have a users table, we have a stack of 8K pages that look like this. If I were to add additional indexes, I would have different stacks that represent those indexes. And for the other tables that we have, like the post table and whatnot, those are different stacks of 8K pages based on the layout of the table in question. Right? The smallest unit, and this is key, the smallest unit for Postgres to be able to think about data, it's not rows or columns, it's actually these 8K pages. Right? When Postgres tries to move data between memory and disk, what it's actually doing is moving 8K pages around. Just like I'm kind of, moving around with my hand, that's what Postgres is doing when it's actually shuffling data around. If you want to read some data in Postgres, well, what Postgres has to do is it has to go figure out which page does that data live on. And then once it figures out which one it lives on, it will pull that off of disk into memory, and then it can give you the information from that page. If you want to write a row, right, same thing. It's got to go find the page in memory. Ideally, it's got to get it into memory if it's on disk, right? Once it has it there, it can mark the rows as modified, whichever row you're changing, and write the new row out, and then it goes and writes that back out to disk, right? Writes the page back out to disk. And so that, tends to work fairly well. I would say in an ideal world, what we would really like is for simple queries that are easy to parse and easy to get the information from, right? If it's easy to understand, if the data is not particularly long, ideally that data fits on only one page. You don't need to get multiple pages to get what you're trying to get. Um, Also, the server would know exactly where that page is. It'd be easy for it to find. And then ideally, it would be in memory. That would also be fantastic. So it could jump just directly to that page, doesn't have to go out to disk, right? That kind of thing. And also, I would say it would be great if it could just return data as is, right? Didn't have to do any manipulation to it along the way. That would be fantastic. I would give you an example, something like if you were to ask Postgres and say, hey, can you go get my profile from the user table, right? Me personally. And it was, oh, sure, I could do that. So I don't have the magnum opus about me. Like you could just dive in, uh, you know, look into the table, get that one page that my data is living on, and return it back to me in and out, super fast, really quick and easy. Everybody's happy, right? That's the ideal world. But of course, if the last 3 years has taught us anything, I think we can all agree the world is not in an ideal place. Right? Often queries aren't easy to understand. Uh, they can get more complicated over time. In my experience, that's usually what happens. The data that you want typically tends to be spread across multiple pages, so it's a little more difficult to pull that together and bring it back. The server often doesn't know exactly what pages it needs. Right? It's going to have to do some hunting around in order to get that. And I also think typically those pages are not in memory. It has to get the data from drives, which are ultimately slow, and sometimes across a network or whatever it is. And I know you're like, well, if it's running real fast or whatever, maybe that's great. I don't know. In my experience, like I said, I think typically you want as much in RAM as you can, but companies have found somehow mathematically it's cheaper to pay DBAs than it is to buy RAM. So, uh, oftentimes it's going to disk one way or the other. Um, and of course, I shouldn't overlook the idea that often the database is going to have to do a lot of work just to give you the data back. Sometimes people want to like have math, operations, arithmetic on pieces of data, aggregating the data. People love their counts. We got to give them their counts. Joins across multiple tables to grab data, ordering that data. I've even seen formatting of data. They want it to look a certain way, return, I don't know, HTML from the database rather than do that in the app. All of these things cause Postgres to do more work, right? If you think about a query like, hey, Postgres, can you give me all the users in Mississippi and also grab their questions? I mean, Postgres is going to look at that query and be like, well, I guess so. I'll have to go figure out where all the users who live in Mississippi, where their data is in the pages that I have, right? And, I don't actually know which questions are there, so I'm going to have to figure out a way to go get the questions as well, and that's certainly going to take some time. That makes nobody particularly happy, although when you get the answer, you'll be happy enough. But it's all, it's more work, and that's not great. So as you try to think like a Postgres, here's the real trick, right? The job of Postgres and the job of you as a Postgres is to think about when you ask a question, how many rows is your query going to need to return? You need to think about which pages might actually have that data in them, right? Is it in a table? Is it in an index? Is it in a different table? Where are we talking about here? You got to think about what's the most efficient way to get those pages, especially given those multiple copies of the data, right? Copy in the index, copy in the table. You also have to figure out if you have more than one table, what order those tables should be processed in. Sometimes it may be faster to look at one table versus the second one. That's important to consider. And all these are factors. We're going to keep it simple for now, right? We're just going to keep it simple for now. But the key thing to understand here is that as you think about how Postgres has to process your questions in order to retrieve the answers, the better you understand that, the better it will help you with query tuning, and also would actually help you with schema design as well, because you can think about, given this schema, what would this look like? What would Postgres do in order to be able to answer the question? So we're going to go through a few exercises where we're going to map out some queries and see how it works. And I want you to think about how you would answer these questions if you were Postgres. We'll keep the first one real simple. I'll walk you through it and we'll see exactly how it goes. Imagine I said, I'd like you to give me all of the IDs from the user table, right? Pretty straightforward query. Select ID from users. You have a stack of 8K pages. I want you to explain how you would do it in plain English, right? Imagine you had a stack of pages just like this. You'd print it out, and you have a stack of them sitting in the copy room in your office. You all remember what offices are, right? Okay, so remember in the office, there was a room, had file cabinets, a printer, copier, whatever thing that was always jammed. Yeah, so you got a stack of these pages in that copy room, right? And I want to know how you would go about answering this question for me, given those sheets of paper. It's not a programming exercise. Like, I don't want to hear about, linked lists or whatever, formula you've got. Like, just in plain English, how would you go about getting this information? Well, I think most people would say, I guess the answer is I would just pick up the stack of pages, right, and start looking at them and say, well, the first ID is -1, it's -1, 1, 2, 3, and just read on down, right? I pick up the page, just read out each ID and yell that out to you to give you your answer. It's pretty straightforward, right? And if you want to look to see what Postgres would do, well, let's take a look. So this is Postgres' execution plan. And one of the first tools that you get introduced when you're trying to understand how Postgres queries work is the explain tool. Most databases have something very much like this. Often they all, it's very common to call it explain. But in any case, this is the tool that you would use. And you just pass the query in to Postgres and say, hey, what is the plan that you're going to use in order to get this data? And here we see it wants to do a sequential scan on the users table. We'd say, hey, that's basically what we were doing, right? We were picking up a piece of paper and we're just sequentially scanning not only that page, reading out the IDs, but also, when we go to the next page, get the next page and the next page thereafter. What's interesting about that is it almost doesn't matter if, what order, where we start in that. If the pages were all shuffled up in the copy room, we just pick the first one and start reading through, and that's all we would have to do. Right, so that's simple enough to understand. Now, I want you to look at this particular plan. And what I've done here is I've passed a couple of extra parameters in to explain. And as you get into more query tuning and trying to debug performance issues and whatnot, these are usually, I would say, the two most common parameters passed into explain and the two most useful ones. And what we're doing is we're passing in the command to explain. We're going to pass in an analyze and a buffers command into explain along with our query. And now what it's going to do is instead of just telling us, here's the approach that I intend to use in order to get your data, I'm actually going to run the query and then tell you what happened, right? And so the analyze part runs the query, and you'll get the time and like the number of rows that were involved in the query as it was being returned to you. And then the buffers is going to give you buffer information, right? Now, buffer information is pretty key to a lot of performance issues. And you might say, well, what's a buffer, right? So a buffer is essentially one 8K page. So Postgres keeps pages in memory. If I said I needed to use one buffer for that query, you would know I used one 8K page. You can see in ours, we actually read about 175,000 pages. So there's a lot of data, right? There's about 12.5 million rows in this users table and 175,000 pages. 175,000 pages is like 350 reams of paper, right? That is quite the copy room if you were to store all that. And I'll tell you, users is not the largest table by far in this database. It's not the smallest, it's decent size, but it's definitely not the largest. So as we're going through these exercises, I want you to keep in mind this idea that, hey, when I'm going to try to figure out these answers, I have to deal with 350 reams of paper. It's not nothing, right? It does make some of this stuff a little bit trickier. So let's try another one here, right? Now I'm going to say I want all the IDs from users who have accessed the system after March 11th of 2020, right? So I've added in where last access date is greater than 2020 March 11th. Okay, how would you go about getting this data? Right, in plain English, no hashes or merges or whatever. Like we're not going to talk about any of that stuff at the moment. Just in plain English, 350 reams of paper. How would you go about answering this question? How would you give me the answer to this? Well, if you think about it, probably the answer should look pretty much like the answer to the previous one with a little bit of a tweak. And you'll note it almost sounds like SQL in this tweak, right? We're going to read through the stack of pages just like we did before, yelling out the ID for each row if, and that's a key if, the last access date in that particular row is after March 11th, 2020, right? We have all the data we need as we scan through these pages, right? We have the ID, we have the last access date, we can put that together and just tell you which ones actually match. Is that what Postgres does? Well, let's take a look. As you can see, yeah, that is what Postgres does, right? It does a sequential scan on the users, just like before. In this case, we have a filter now that has been added, right? And you'll see that we're filtering on last access date, greater than March 11th, 2020. So that filter happens, which a little bit of extra work in there. And then you'll see we remove a bunch of rows and whatnot, and we actually only return now under about 3 million rows, so around 3 million. But pay attention to, right, so 3 million versus 12 million, but pay attention to the buffers piece. If you look at this, we basically are still in that 175,000 pages range, right? We're right using the same basic number of buffers that we used the last time. Just because we've returned fewer rows doesn't mean we actually had to do less work, right? Adding a where clause to a query with no matching index means we're going to have to scan all the data to understand whether or not we can return those rows. If you're trying to figure out if a query is more expensive or not based on what you're adding into the query or removing from the query, you might say, well, how do I know for sure? Like I would have thought I'm giving fewer rows, right? And I hear this a fair amount. I'm only returning 10 rows. Why is it so expensive, right? It's not about the number of rows. It's about the work you have to do in order to find those rows. And a large part of that is going to be how much data does Postgres have to look through in order to give you those rows, right? So if you're trying to figure out how do I know whether a query is going to be more expensive or less expensive, one good way to do it is to actually look at those buffers, right? If these two queries are reading all the same number of buffers, they're going to be relatively similar. Might be more or less expensive based on some other factors, right? There is some CPU overhead in there. But you can run both of those queries and look at the buffer counts and see, okay, this is going to be more expensive if I do it this way. Now, the thing that's actually magical about databases, right, is that while we can kind of run both queries and compare the buffer output and see which one is doing more work, databases actually have to figure out how they're going to run these queries without actually executing the query, right? Before they execute the query, they can't say like, oh, I've got a plan, I'm going to go execute on it, and then, if it's right, or if it's wrong, I'll bail out and then try a different plan. Nah, they got to figure it out before they even go and try to do the work. That's much trickier, right? And you said, well, how does Postgres actually do that? What's the mechanism? How does it know? Postgres knows. Well, the thing that we didn't mention on those previous slides that you probably saw was there are these cost columns. And if you compare the two execution plans from our first query, where we just want all the IDs, or from the second query, where we want the last filtered on the last access date, you'll see that both have a cost. They start at 0 and it ranges up to about 300,000 on the first one and 333,000 the second one. So it's about 10% more expensive in Postgres's estimate for that second query. And one of the key things here is that these are estimates. right? This comes from the fact that we have to do this filter, right? We know we're going to do a little bit more work because we actually have to look at the data. Before, I didn't have to look over the page, right? Like I could take my page and look at it and say, okay, I'm just reading down, the ID columns. Like it's I don't have to look at the other. Now I kind of got to go back and forth, and that's not a lot of work, but it is going to take some extra time, just for my eyes to scan back and forth and tell you which one is the right one. So, what does cost actually mean, though? Right? That usually is kind of the next question people wonder. Like, I can see the cost is more; it's 10% higher. So, what does that translate into exactly? Uh, and this is one of those things that's you just kind of got to learn to accept it. Cost does not actually mean anything, not in Postgres land. It's based on a sort of theoretical amount of work that would represent one sequential page read. That's a cost of one would mean I got to read one page basically, and then everything else is sort of computed based off of what we assume the relative amount of work is to that piece of work. Right? It does not directly correlate to time or IOPS or CPU instructions. Those things are related, right? It is Postgres's estimation of the amount of CPU and IO work, but it doesn't translate directly to that. It is not, it's not a direct representation of any of those things. And if you think about it, like you'd say, oh, well, could it be like a disk IOP, right? Like if I have to do more disk IOPS, it's going to be more expensive. Well, it's probably true. But on the other hand, from Postgres' point of view, to actually know what's going on at the disk level is pretty difficult. Postgres outsources much of the work that it does to the operating system. Like all good companies, it tries to outsource to cheaper labor, something like that. So it outsources this work to the operating system. And when it says like, hey, I'm going to do disk I/O, like it knows it had to read from disk. But what it doesn't really know is like, when I say disk, do I mean the kernel's file system cache, right, that it might have, or the file system might have its own cache as well? Does the storage array that I'm talking to actually have, battery back cache there? Am I talking over a network maybe? And so there's network latency in there. Right? I know I had to do a disk IOP. I don't really understand what that means as a database to say I did a disk IOP, other than I didn't have it in my memory. I went to the OS and asked. I don't know where the OS got that from. Right? So that makes it a little bit tricky to think of cost in anything that is directly attributable to something technical that you could measure from the operating system. Right? So you just have to kind of get used to that. There's a term that I've heard before that I really like called query bucks. And this was first coined, from my understanding, from Kendra Little. And, it sort of refers to this idea because we use the term cost, which is what the database calls it. But the cost isn't actual, money. It's not real money. It's, we're in the world of cryptocurrencies, right? Everybody can make up their own money. But the cost on any one machine, and this is important, like the cost of a Postgres is not the same as cost in Oracle or SQL Server. The cost in Postgres is not even the same as, it does not directly correlate to the same cost of a Postgres on a different server, right? Or a different version or anything like that. Right? That cost, it's a made up currency that's pretty specific to the machine that you're running the thing on at the time. And that's fine. If you want to know, compare one query to another on the same machine, that works pretty well. When you start going across machines or talk, to somebody else in might have different architecture or whatever, it really breaks down quickly, right? It's like how many Dogecoin are equal to the number of lolcat bits or whatever, right? Like it falls apart really quickly as an abstraction if you try to make it more than just that abstraction. So we do talk about costs a lot, and it's a very cheap way because you can generate and see what Postgres' cost is going to be with explain without having to run a query. So it's a cheap way to get a relative idea of how expensive it is. And I would say typically if you reduce the cost by doing something, if you change a query and you cut the cost in half on, like your workstation, those same changes should have a similar effect when you take it into production. The numbers may not match up, but for a relative idea of what am I doing to the query and am I making it better, it should work for that purpose. So keep that in mind. All right, so now we've talked about costs and looked at that. Let's add a little bit more into this query. and see where it takes us. Now I'm going to ask, instead of just giving me the IDs of those people from March of 2020 and beyond, I'd also like to get those IDs in the order of their last access date. Right? So I'd like to get those IDs now, not just random. I'd like them ordered by that. So only the ones that are recent, but also in the order of their recency. Now, as you can imagine, that's going to raise costs on the query. But first, before we worry about that, let's first talk about, in English, how would you solve this query? Right? What would be the plan that you would do in order to achieve this? Well, you're probably thinking very similarly. Like I sort of have that sequential scan tool in my tool belt. It's the only one that has. I'm probably going to do that. I've got to do some filtering. And when I filter those rows, I could probably sort them in memory maybe, right? And then I can return them to you. And I want to say, I like where you're going, but you're not quite there yet, right? The idea that you're going to sort it in memory is great. But the problem is most people, right? And we're talking about people, right? You're going in, you got your page, you're reading off the page, you're looking at the last access date, and you're going to try to keep that in memory. Most people can only remember, 7 to 10 numbers tops. Like that's it. Any more than that, and you'll start to forget them. And I'm not saying that you're not smarter than most people, right? You're obviously smart. You're listening to this talk. And so, you got to be smarter than the average bear right there. But, 20 numbers tops is all you're going to do. And we know there's going to be 2 million plus rows coming back. So, even you're not that smart. So, sorry. So you need to do something other than just try to sort that in memory. Right? Well, okay, so what could we do? Well, if we think through it, we read through our stack of pages. We make notes with some of the fields in there. Now, we need to know the ID, so we're going to put that on our note for the ones that are newer than March 11th, 2020. Right, so we're going to write that down. But then actually to sort those records, we're also going to need to know what the last access date was. It's not just enough to know it was newer than that. We actually need to know what it was. So we would probably have to write down the ID and the access date field. Right, and if we had both of those, if we put it on, get a little post-it notes and we write down that data, and then we could move those around and sort them and be able to read that back out. All right, but we probably have to have both fields. Well, let's go ahead and see what Postgres wants to do about that, right? As you can see, so we've adding that order by, we now have a considerably more complicated explain plan. And so let me break this down a little bit for you first, right? So the first thing is when you look at an explain plan in Postgres, and there's other tools out there that will display this differently, but this is the basic one that you should always be able to get because this is the one that comes back if you run it in SQL. Right, so if I do explain analyze buffers on this query, first thing is we start from the bottom and sort of innermost piece and read that. So the first step here is we do a sequential scan on users. And Postgres actually parallelizes this, but we don't have to worry about that at the moment. So we do that sequential scan on users. And then we actually are going to work our way back up and to the left. So we go from the sequential scan on users up to a sort operation, and then from the sort it goes up to the gather merge operation. And two things about that. The first one is that each of these steps within the plan, each node is almost like its own little program, right? It has an input, it has an output. It's responsible for one thing, right? You had one job. So in the case of parallel sequential scan, like its job is to go get the data from the user table sequentially, right, and pull that data back. And then it's going to hand that off to the sort operator, which is going to actually do the sorting of the data. And you can think about those little arrows in there as like, this is where I got my data from, right? The sort's getting it from the parallel sequential scan, gather merge is getting it from the sort. So that's the sorted output. We did mention, right, we thought our costs would go up. So I want you to look at this and you see that now the basis at the end, by the time we get to the gather merge, right, this cost amount now is ranging from $378,000 to $646,000. In case you couldn't remember, maybe you used all your memory up and didn't put it on a post-it note, In our previous query, the total was 333,000 as a cost. Right now, we're talking 646,000. We doubled the cost that Postgres expects from having to deal with this query by adding in that order by. And you might think like, well, I mean, we did expect more work. Why is it twice as much work? Where does that come from? Is it the parallelization? No, that's not it. Like, it's still reading the same number of pages there, and whatnot. So where is that extra work coming from? Well, the biggest part is actually in that sort step, right? That second piece of our puzzle. And again, we've got a sort step. It's sorting by last access date because we need to get the data, right? We want the IDs in the last access date order. But here we talk about the sort method that we're going to use. And in this case, what it ends up doing is it has to use an external merge, which means it actually had to go to disk, right? It had to write those down. It couldn't keep it all in memory. It had to go and write it on post-it notes. And Postgres is probably a lot like many of you out there. It has a little more bravado than it should. When it first starts, it will actually try to do this in memory, right? There's a sort of a configurable amount of memory you can designate to a query. But if it runs out along the way, like it says, no, you know what, I can't, I'm sorry, this is like number 12 of the numbers that I have to remember, and I got 2 million more to go, like, give me the post-it notes, I need to write this down. All right, so once it starts writing that stuff down, now it's got to write that data out, it's writing its post-its, then it has to sort that and give it back to us, right? In this case, we have written out 24 megs of data, right, that have been written into the post-it notes, quote unquote, that Postgres has had to use. So we had to write 24 megs of data to return the answer to our question. That's a fair amount of data to have to write and then read back out, right, and pass along to the gather merge bit. If I were to change one thing about this query, such as instead of asking for the ID, what if I were to say, I'd like all the columns, right? All the columns. What would happen? How do you think that would actually affect the work that would need to be done in order to answer this question, right? Switching from a select ID to select star. Well, you probably would say, well, I think we can use a pretty similar plan of attack. We do our sequential scan to get our data. We do our filter, right, for last access. And then in that order step, there's the question, right? So maybe we write down our ID and our access date, we can sort it, and then go grab the rest of the data that we need to return the information. And that's certainly an option. But as it turns out, that's not how it really works in Postgres. In Postgres, and the way that this works is when it goes to write that down, it can't just write down the ID and the access date. It actually is going to write down all the data from every column that it's going to need to answer that question. Right? It's going to write down the about me, the display name, the last access, the location. Right? It's going to put all those into its temp files, onto its post-it notes, in order to answer the question. And then it takes all that data and it sorts all of it by last access date, just like we did with just the ID, but it sorts all of those rows of data, right, much larger now, in order to do that. If we look at Postgres' execution plan, again, it looks pretty similar, sequential scan, pass into the sort, but the big thing that jumps out at us now is, boy, that sort, external merge, instead of doing 24 megs of this, which we already thought, that's a pretty sizable chunk of data they have to read and write to answer a question. Now it actually is writing over 100 megs of data. Excuse me. That's quite a bit more. It's hard to argue with that. All right, it's doing way more work than it did before. And I hope everyone can agree with the idea that, doing more work sucks. Like, we would ideally not have to do as much work. It's simple to say doing more work sucks, but let's talk about why doing more work sucks, or in particular, what about this change has made this suck so badly? Well, first off, are we doing more work to read the data? We have to scan the entire table in both cases, either way. So you'd say, well, that's not really doing that much more work. But that may be an astute watcher would say, what about that about me column? Now, you said it stores some of that data in a page someplace else. And so if you ask for all the columns, don't I have to go get that data in order to return it back? And the answer is yes, you do have to do that. So there is more work actually going on if you ask for all the columns. It's not huge, but there's some, and let's not forget about that. Am I doing more work to write the data? Well, we clearly saw we went from 24 to over 100 megs of post-it notes that we had to put. There's a lot more stacks of post-it notes that you got to sort through, right? You may have been able to write, I don't know, multiple lines for sure of IDs and access dates in the simple version of that. But when you ask for all the fields, you may not get more than 1 or 2 entries of post-it note at best, right? And maybe you got the larger post-it notes, but still, you're going to be writing down a lot of stuff. Are we doing more work to sort that data? Well, if you can imagine 4 times the number of post-it notes or 24 to 100 megs of data that we've written down, definitely going to take more sort operations to figure all that out, right? We're sorting way more post-it notes than we did before. So there's a lot more disk IOPS that are going to happen. So that's definitely going to be more work. And then are we doing more work to output the data? Well, we are outputting more data, not more rows, right? The number of rows stays the same. That doesn't actually change at all. But now we're giving all of those columns. So we're definitely giving you more data back. And I often see people actually focus on this last point probably too much. You'll hear somebody say, you're returning all those columns. It's way too much data. Right? We really shouldn't be doing that. But I would tell you, network overhead is actually pretty cheap. When you see a problem where, we're returning way too many rows, that's one thing, right? That's the size of the data overall. And if you don't need those rows, trimming that down is one thing. But to say, we just have too many columns, the difference per row for any given column is not quite as much. Network overhead, like I said, it's cheap. Don't typically bottleneck on network. Okay. Here's that execution plan again with the rows highlighted. We're still talking under 3 million. But it is 5x the amount of data, right? If we look at the number of buffers, it's way more buffers that we had to write in order to do that. The cost also goes up as expected. We were at 660,000-ish before. We're now over 800,000. That makes sense. The cost is going to go up because we're now doing way more I/O and way more CPU to figure that out. And there's a little hint I've highlighted here. You see that width equals 153. The width column is not something that you typically focus on, but it's sometimes worth taking a look at. That is actually the number of bytes that are needed in order to return the non-metadata columns in the pages that we're looking at. Right? So previously we would have an int and a last access date, so it would be about 12. Now we're talking 153, right? So it's a 12x factor on the width piece. So that's a hint that we're going to actually be dealing with much more data being passed through these different operators as we work through our query plan, right? These are the things that are really expensive, right? Reading and writing to disk on your database server, that is what really kills performance. That's the first thing you really have to go for. A lot of people who want to die on the, don't ever select star hill. I guess maybe I will put it another way. If there's an ORM that is maybe filling in all the fields for a given table automatically, right? You got 20 programmers and you got 1 DBA. If the programmers say, we need that so we can code features much faster, who you think management's going to side with, right? Don't die on the select star hill. It's not where you want to die. You don't want to die on that hill. You do want to remember, though, sorting data is expensive, right? You have to be careful with that. And the more fields you add, it is more expensive. We just shown it was more expensive. You could take that example and show that to anybody on your team and say, look, just remember, it's more expensive. If your queries were just one table, there were no joins, you didn't have any order bys, I would say you could select star all day long. But once you start adding order bys, especially, that is where it gets really dangerous. As you have more and more concurrent queries, right? That's more and more concurrent write activity that has happened. And this is for selects. This is not actually trying to write any data. We're just trying to answer some questions. While Postgres is free as in beer, it isn't free as in hardware. You have to remember that. So when you do these more expensive operations, it does cost you in the long run, not just in a magical query box kind of way, but in actual dollars, either on your AWS bill or on your hardware bill, right? Keep those things in mind. If you need an alternative way to sort data that is actually cheap, because it's not cheap to do it on a database server, move that out into the application tier, right? Throw it onto your scalable web servers. It's easy to spin up 10 more web servers. It is not easy to pay DBAs to try to figure out how to solve bottlenecks on a shared production database server. That is not an easy task. Web tier is made for that kind of thing. And I often hear complaints and pushback on this, like, hey, like it's just one query, right? Like it's okay to do it. Maybe I'm not going to do it all the time, but I just need to do it this one time. And the problem with that is that what we know about modern applications and the way they work is it's never just one query, right? Our applications are designed to run the same query over and over and over again. And when you do that, right, and we can simulate that, what does that look like if you're just going to run the same query over and over again? Well, in PSQL, there's a command called /watch, and if I pass it a 1, it'll run that same query every 1 second, right? So if I were to pass our query in with the select star and order by on the last access into the watch 1 command, it's going to run that every 1 second. What does that mean as far as execution? How does that change what Postgres does? Well, you might think, well, it's still got to read through the stack, right? It's got to read through all those 8K pages. It's got to make a note, right? It's got to take what we see in here, write down on our post-it note all the fields for each row, if the last access date is greater than March 11th, 2020. We sort all that data, right? We just did all this work. So maybe we could hold on to the data in case we get the same query. Yeah, we know it's coming in 1 second, right? We know that query is coming back. So just hold the data for now, and we can send you the same data back the next time around. Well, as it turns out, again, that's not how it works. We're working with Postgres. Postgres is great. It's my favorite database. It's the one I would pick over all others. But it doesn't have every feature out there, right? It has some features that other databases don't have, and I love those features. That's why I love Postgres. It's a big part of it. One feature in particular it doesn't have, though, that Oracle does have, is something called result set caching. Other systems, try to mimic this type of a thing. But there's a reason that Oracle costs, I don't know, $40,000 a server, last I heard, right? It's not that that's always useful, this result set caching, but it can be sometimes, right? In most cases, it probably isn't useful at all. But it definitely is sometimes, and that's why they charge what they charge, right? And if you think about it, Oracle has a pretty spiffy sailboat racing team. Larry has an island. You'd like to see your license money go into something tangible. And then, there's an Enterprise DB island that you can go vacation on, right? So if you're going to spend the money on licensing, get some features like that. But we don't have those features in Postgres, right? That's not one that is out there. Nobody's even working on that. So if you don't have that, then what is Postgres actually doing? Well, if you run that query over and over and over again, every time it runs, Postgres is going to read all those pages, right? It's going to look through all of those. It's going to write all that post-it notes out, sort all that data, return it to you every time. You run it 1 second, read, write, sort, return. Run it the next second, read, write, sort, return, every time. Eventually your system catches fire and it burns to the ground and then you don't have to worry about it anymore. But then you got a different problem, right? You could run that query over and over again. Even if you're the only person on the system, Postgres does all that work every time, right? It doesn't matter if nobody else is writing, if the data hasn't changed, it's going to do all that work every time. Even if the whole table were to be able to fit in RAM, the temp files are not going to fit in RAM. Postgres is going to have to write those out every time. Even if you did it twice in the same session, you connect, you run the query again on the same connection, it's still going to do all that again. Even if you did it in the same transaction, Postgres is going to read all the data, write out those temp files, sort that data, return it back to you every time. So you got to remember that, right? Postgres is caching 8K data pages at best. There's a thing where people say, oh, I run this query the second time, it's faster. Oh, that's because the results are in cache. I've heard people say that. Developers say that a lot. I guess it's the results are in cache fallacy. It's really more of a misunderstanding. The data pages that your answers live on may now be in shared buffers in Postgres. So it may look faster, right? But Postgres is not caching rows or tables, and it's definitely not caching query results, right? It just maybe has moved some of these pages from down on disk over into memory. And it'll be faster because reading it out of memory will be faster than reading it from disk. But again, temp files are going to be written and sorted, and all of that is going to take place touching the file system. If that happens, your performance is going to suffer. There's no other way around it, right? So thinking about that, all right, look, you told us why so many things can be bad and why it can be slow. I'm sure what you're really now wondering is, how do I make things go faster? Well, first off, let's think about what we talked about. I want to make sure that you're getting this, right? First off, what have we learned? Well, you can use the explain to see Postgres' query plans. Simple, easy, works on any query. You can use explain with analyze and buffers to see how many 8K pages are involved, to actually see the physical amount of work that is needed to be done for Postgres. If you add a where clause to your query, you might reduce the number of rows that are returned, but it doesn't necessarily mean you reduce the amount of work, right? A where without a supporting index is still going to lead to a sequential scan. It's got to evaluate on every row that is involved here. So, same thing with order bys. Order bys without supporting index, that's often worse, because that's not just scanning the data and evaluating it. Now you're writing temp files and having to sort that data, send it back. You have to watch out for that. Those are key things to be looking for when you're finding performance problems. And finally, the one thing I hope you really do get out of this, remember, Postgres is caching 8K pages, not rows and tables, not query results. It thinks about things in 8K pages. How much work is it to get those pages, to find those pages? What do I have to do with those pages in order to give you a result? That's what Postgres is worrying about. That's what its memory is focused on, is 8K pages. That's actually where we're going to stop for now. I know you're thinking, oh, wait a minute. I thought you were going to tell me how to make things go faster. That's part 2. But if you liked what you saw in part 1, I'm happy to put some effort into getting you to part 2 and let you know. You can follow me on Twitter at @RobTreat2 or send me a message. If you think this was useful, if you'd love to see part 2, we can make that happen. Hope you enjoyed it. I'll talk to you later.